Okay, so this is the new Technologies in Mathematics seminar. I'm Mike Douglas. And today we're very pleased to have Jason Rute of CIBO Technologies and CMU before that, who will speak on neural theorem proving and lean using PACT. And Jason, please.
Thank you. And thanks for inviting us to speak about our research at this seminar. So this talk, sorry, my keyboard, that was weird. Give me a second. I am having slight technical problems.
Just now.
There we go. That was weird. My keyboard wasn't working. Okay. So this talk is going to be research with Jesse Michael Hahn at University of Pittsburgh, myself, Tony Wu at University of Toronto, Ed Ayers, University of Cambridge, and Stan Palu at OpenAI. And we also wanted to thank the formal team for many discussions at Google AI. So this talk concerns the lean theorem prover. And I know some of you are familiar with lean and interactive theorem proving, and some of you are not. So let me talk a little bit about interactive and formal theorem proving. So the idea of formal theorem proving and interactive theorem proving is that, in theory at least, one can take a mathematical proof and check it, mechanically check it down to a bunch of simple rules. You know, people are usually familiar with Zermel-Fraenkel set theory, but there's other systems too, like dependent type theory that we'll be using. And there's many motivations for this. Bertrand Russell and Whitehead, you know, they had their Principia Mathematica, where they tried to do this. But with the advent of computers, this has become much more feasible, and especially with the advent of just social networks and ways to collaborate on large software projects, this has become much more feasible. And some people have the desire to digitalize mathematics, to unify mathematics into like kind of a common knowledge base. This can be used to prove the correctness of software and hardware. And by adding more mathematics to these systems, you're also able to use that mathematics to then prove the correctness of maybe more complicated algorithms. Also, it just makes mathematics accessible to computers in a new way. And really, the fact that you know, many people have spent a lot of time on this has made this project possible. But then hopefully it's a virtuous loop where we can then bring these tools back to help users of these systems. This work, in many ways, it isn't particular to a theorem prover in theory, but in practice, we use the lean theorem prover, and we really like the lean theorem prover. It's a fairly new theorem prover. It was, I think, developed in 2013, and it's pretty popular and newsworthy. It shows up in certain articles. It has a lot of resources to help you learn it. One fun one is something called the natural number game, but lots of tutorials as well. It has a pretty active user base, and a lot of us like to discuss lean on a chat forum called Zulip, which it makes very nice to just be able to talk to people about your questions. It has a pretty extensive mathematical library called MathLib. It also has been used to formalize other pretty advanced things, such as the forcing proof of the consistency of ZFC minus CH minus the continuum hypothesis. Also formalize the definition of perfectoid spaces, which is a pretty advanced topic. It has a lot of great tools for customization. It has a pretty good meta-programming framework built right into lean. It has integration with Visual Studio Code, which is a pretty common editor, as well as Emacs and other tools, which were very useful for this project. And while this isn't specific to this project because it's in Lean 4, Lean 4 is going to be the setting of something called the IMO Grand Challenge. And I think that has piqued a lot of people's interest in Lean, especially in relation to projects such as this one. This is kind of a pedantic slide, but I just want to disambiguate which version of Lean we're talking about here. So there's Lean is a project of Microsoft Research under Leo Demora, and they've developed it, you know, from Lean 1 to Lean 2 to Lean 3. And in Lean 3.4.2, they stopped working on Lean 3 to develop Lean 4. which is in some sense very different. It's not going to be extremely compatible. But a lot of work has been put at the time into developing a mathematical library called MathLib in Lean 3. So the Lean community has taken over the development of Lean 3 while Lean 4 is getting ready. So this work concerns the Lean community version of Lean 3, which you can find at these websites. And also, if you go to the Zulip chat, you can talk about any version of Lean, and people would be happy to help you and clarify any confusion you might have. Okay, I want to give a demo now of both Lean and the tool that we're going to talk about today that we've added to Lean or made available to Lean users. So as I mentioned, Lean is a way to prove theorems mechanically, where the computer will check that your theorem is correct. And it's still, for the most part, a user will type in the theorem, but Lean offers a lot of help in that regard. So for those who are not familiar, I'm going to give a very simple example. This is not the sort of example that a typical Lean user would be proving, but let's say we want to prove that for all integers, a plus 5 equals 0 implies a equals -5. Again, a very simple result. And we're going to prove it. As you might imagine, there's something like this in the library, obviously not with a 5 in it. And this is what this is right here. So I'm putting my cursor over it. And there's a lot of kind of gobbledygook at the top, but what it says is that if you have an additive group G and two elements A and B in that additive group, then A plus B equals 0 implies A equals -B. And there's simpler ways to just straight up use this lemma, but just for the sake of kind of showing how Lean works, let me type this out a little more explicitly, as if I'm kind of teaching an introduction to proof class. So if you want to prove a for all, as I would say when I taught introduction to proofs, I would say, well, just take an arbitrary element A and Z and then try to prove something about it. So you can do that in Lean with this intro thing. Now, I should step back here for a second. What I'm doing is what's called a tactic proof. And if I put my cursor in between this begin and end block, it'll tell me the thing I'm trying to prove. This is the goal. And after I type in my tactic, that goal changes. And now instead of saying for all A is moved up here to the local context. And so we just have this arbitrary element A that's an integer in the local context. And now what we want to prove is an if-then. And as I've told my students, if you want to prove an if-then, we'll assume the if and prove the then. You again do that with an intro. And now we've given a name H to this fact, or this assumption, A plus 5 equals 0. And one way to think about it is, instead of a name, you can kind of think about it as some sort of witness to this fact or proof that A plus 5 equals 0, that we assume we have that. Now here's where we're actually going to use our fact that we already have, and we can apply it. So I'm just going to copy and paste this fact. And by applying it, what Lean realizes is that the conclusion of this fact and the thing we were trying to prove right here, A equals -5, are basically the same, except for there was a few assumptions that you needed to satisfy for that to hold. So now it wants us to satisfy that assumption, which is that A plus 5 equals 0. That's easy to satisfy because we have it right up here. And I put a comma there, and now it says goals accomplished, which if you've never done automatic theorem proving or interactive theorem proving, the minute you get that, you just put your hands up in the air and you get very excited. So Lean doesn't store the proof in this format. This is called the tactic proof. What Lean stores the proof, and let me show you by giving the proof a name. I'm going to call it my example, and then I'm going to print it. There you go. Lean stores the proof, if you see over here, in a different format. And if you're familiar with functional programming or type theory, you'd recognize this as some kind of term, and it's called a proof term. And it's just another way to write proofs. And it's really kind of underneath the surface how Lean represents things as proofs. And I'll just give a really quick tour of that because it'll matter a little bit for what we do here as well. So if I want to write a term proof, I don't use a begin end block. I just write the proof. And Lean offers this kind of helpful thing that at any point in the proof, when I'm like, okay, what do I type here? If I put an underscore, it'll tell me what I need to fill in. So here it says you need to give a proof of this fact, which is obvious because that's the fact I'm trying to prove. And the way you prove a for all, the most direct way, is with a lambda, which if you're familiar with functional programming, this might sound kind of familiar. And then again, I can use an underscore to tell me what I need to. Sorry, it's been a little slow today.
The parenthesis has to go after the lambda.
Oh my goodness, yes, thank you, thank you, thank you. This is the danger of a live demo. And now I want to prove the if then. I can also do that with a lambda. Now I want to prove this. I'm going to use this fact. Now, the way you can think about this fact is it says that if you give me a proof, it's sort of like a function. If you give me the proof of this first thing, then I can give you a proof of the second thing. And so now we just need to figure out what argument to give our function. And that argument is exactly this h that we have. So we can just give that. And one thing that's interesting is even though these are two very different proof modes, there's sort of a trick with tactic proofs that if you ever want to give a term proof when you're in the tactic proof mode, you just can use this exact tactic. So exact right here, and then put in your term proof, and you get or your proof term, and then it works. I'll show it works by putting a comma here, and there you go. Now, I don't expect if this is your first time seeing Lean that you're going to be a Lean user after this demo, but the point I want to get across is there's these two ways to prove things. There's the tactic proofs and there's the term proofs. Lean stores things with term proofs. And the exact tactic is a way to write a term proof inside tactic mode. Now, tactics, the tactics I've shown so far are just very low level, and all they're doing is sort of the exact same sort of things that the term proof does, like lambdas and function application. But each of these tactics is really a meta program that can be arbitrarily complicated, and you could write any sort of mathematical decision procedure or algorithm you'd like in a tactic if you just take the time to write it. And Lean has a pretty nice meta programming language for doing exactly that. And the Lean users have made a lot of powerful tactics that do things like that. One tactic called tidy is basically, if you know what you have to do is just follow your nose and do the obvious thing every step. The tidy tactic does that. So this first line here isn't that important. I just took this fact that we were using in the library and I just kind of forced it to go in the local context here. So the tactic now knows that I want to use this fact. And now if I just uncomment this and use the tidy tactic, it solves it. That was a little awkward to do it with that. There's another tactic called finish, which has just the same sort of thing, but it has a little better interface. And again, that solves it. Now you might say this fact is obvious. Even like a middle schooler knows this. And the integers are so well understood that someone had to have written a tactic that just does this sort of basic integer reasoning. I mean, this is even a decidable theory, the theory of the additive theory of integers. And sure enough, someone has. It's called omega. And that solves these sort of basic problems with the integers. But of course, that's because we're working with the integers. What if we were working with something that's a little less mainstream? Did someone take the time to write out the decision procedure, even if we know it exists? Maybe it's just a lot of work to code it up. Really, honestly, the hardest thing about solving this problem was going through the library and figuring out what this dang lemma was that I needed to use. And there is a nice tool for that in Lean called library search. And it takes a little bit of time because it searches through all the library, at least all the library that's loaded into memory. And and it has this nice try this syntax too. So if I just click on this, it'll replace library search with this thing, with this other thing. And that's good because I don't want to leave library search in my code. I just wanted to use it as a helper for finding the thing I wanted. Usually when there's a try this, it'll actually work. This time it didn't because it got a little confused about all this additive group stuff. So I'll just fix that. However, library search can be a bit finicky. You know, this was what I did a library search on before was just a general theorem about integers a and b, but now I just made it a little more specialized where b is 5. And library search, oh, it did find it just because I labeled this theorem up here, but let's unlabel that theorem. It doesn't have a name in the library anymore. And now if we do library search, we'll see that it fails, that it can't actually find this theorem because the theorem it knows about in the library is it's a little too different that it doesn't recognize it. Okay, so what we've done is made a tactic, a tool that applies machine learning, and I'll talk more about how we implement it to help users predict what the next tactic should be. So here is a goal. Here's our goal. And then this goal, we're going to feed into a machine learning algorithm, a neural network, and it's going to spit out a bunch of suggested tactics. And I'll show you an example here. And here's all the different suggestions. Now, some of these won't actually, like they'll instantly fail. So we've just filtered them to the ones that succeed. And in this case, it's pretty confident that what you want to do is some sort of intro thing. So we'll do this one since we're familiar with it from the proof above. And then we'll do GPT-f again. And I should mention that GPT-f is non-deterministic, which is very dangerous in a live demo. But at the same time, I have a lot of confidence that it knows how to do the examples I've given it. So it realizes that we need to apply this theorem. It also helpfully realizes that maybe a rewrite is a little more direct way to apply it. So let's do that, and we instantly solve it. Now, given kind of this, you're like, oh, there's probably just a way to like just type this in directly using exact. And we can prompt GPT-f to do that by telling it a prefix that we want it to give. And this prefix says, okay, your tactic has to start with this. And usually this works pretty well. This is, but the nice thing about it being non-deterministic is if it doesn't work, you just try again. Okay. You know, again, the danger of live demos. There we go.
So here you can tell that it wants to try using a rewrite from all the eq.mprs.
Yeah. So, but yeah, okay. So it did work finally with a few tries. And one thing that's really nice about our approach is our algorithm just predicts what the tactic looks like as text. And what that means is we're not forcing the tactic into any kind of template, which a lot of these other, there are other similar tools out there in other theorem provers, but a lot of them will force the tactic to either look like one that's already in the library or to kind of fit a very specialized template pattern. But what we're doing is just saying, just dream up some tactic and see if it works. And what that's pretty good for is solving existentials, because with an existential, you have to find a witness, and that witness doesn't have a very clearly defined form. It just is the term that works. So in this example, okay, so again, this doesn't always work. This is really the danger of a live demo, but that's fine, because I know if I just do it a few times, it'll work.
Isn't that a bit of a problem for the user? It's not as patient and doesn't.
Yeah. I think you know, these systems can obviously be improved, and there's some things. I mean, we'll show later that we'll give some hard numbers that this is actually it does solve a lot of theorems that if you let it work. So it's and it did eventually find n+1. And then GPT-f, we can solve it now. And now it realizes, oh, here's the proof of n+1. This one sometimes works right away. Sometimes it takes a few tries. Obviously, the answer here is 4. Whoops. Oh, sorry. There we go. First try. And to show it's just not about natural numbers, here's another example. Okay, great. It solved it right away. That what it needs to do is do the inverse. And notice it doesn't just say, oh, well, here's the witness. It gives the witness, the entire proof, all the special syntax you need by Lean. So it is capable of doing a lot. Here it does nested tactics. So it is capable of a lot, although it isn't always perfect. So I showed a demo of what this is. Now I want to show how it works, and how we built it and what's behind it. So this is an instance of autoregressive language modeling, and you're probably most familiar with autoregressive language modeling in the context of you type in a query into Google, and Google will try to fill in the rest of the query, or you start typing a text message, and your phone is going to try to fill in the rest of the text message, or same thing with email nowadays. And so it's basically just sentence completion. Now, this sort of thing has gotten much better in the last few years due to the invention of a type of neural network called the transformer. And the most famous examples of this are probably the GPT-2 and GPT-3 models by OpenAI. Hence the name of our tool, GPT. And what they do is, again, at least the well-known examples were trained on English language from the internet, large amounts of English language from the internet, and then they're pretty good at giving realistic sounding completions to sentences or paragraphs. So for example, I put in one of these systems, not GPT, but a different one that was freely available on the internet. I said, today there will be a talk at the New Technologies and Mathematics Seminar on neural theorem proving in Lean using proof artifact co-training language models. And it helpfully fills in that this talk is going to be delivered by some French mathematician who doesn't exist, and who's the director of some group who doesn't exist. But I did realize that if it's a French mathematician, it should probably have a French name. And it very helpfully said that this talk will explore how applications of machine learning may help in the proof exploration of elegant theorems, including foundations, differential equations, topology, and group theory, which I think is a pretty good description of this talk. So if these systems are so good at natural language with all its messiness, you think that they'd be pretty good at least approaching more formal language like something like Lean. And now it might not be completely obvious how one uses an autoregressive language model, because what we really want is something called a sequence-to-sequence model, where we give it an input sequence, in this case, the goal, which is a sequence of characters or a sequence of words, or we're using something in between called tokens, or a type of tokens. And then it'll output another sequence, which is the tactic. But you can just do that with an autoregressive language model by just saying, here is a special token, which means I'm going to give you the input, and then you give the input, and then here's a special token, and then I give you the output. And you train your model on many thousands of these examples, and then at inference time you just cut off, or you put in a new goal, and you only put it up to this second token that says here's where the output's going to start, and then the model will dream up the rest, and that'll be the output. And what the model does is it predicts a probability distribution over what the next word's going to be, and it keeps doing that every time, and it's autoregressive in the sense that every time it's predicted a new word, it puts that back into the input as to help predict what the next word's going to be. And I'll explain it more at the end about the exact model we use and its size and stuff like that. But that's the main idea. Now, as far as the data set goes, let me talk a little bit about that. So we already said that there's two proof modes in Lean. There's tactic proofs and there's term proofs. And again, tactic proofs are a very common way for Lean users to interact with Lean, but what Lean stores is always the term term proof. So for tactic proofs, what we need for Lean, for this project, for the Lean GPT-f project, is we need the tactic string as the user typed it, so the human written tactic string in the code, and then also the goals, which is also called the tactic state. So we need the tactic state that happens right before that the user typed that. So that's the prompt. We also want the declaration name or the name of the theorem because that'll just help us organize our library. Now we were able to get that information. It wasn't particularly easy because the only way to really, the Lean parser, it has this interesting behavior that it changes as you write code. Like you can write code that changes the behavior of the Lean parser, especially with tactics, which makes it very hard to parse Lean unless you re-implement Lean. But we found a way to make it work where we can get all this data, and we have about 140,000 roughly human written tactical pairs, and about 19, which encompasses about 19,000 tactic proved theorems. Although there's other theorems that are also in MathLib and Lean core that are not proved by tactics. I'll talk about those in a second. I didn't know who was going to be on this talk today, but I know there's other machine learning researchers who are interested in this sort of data, and they might not want just tactics represented as text, and there's a lot of other information that can be gotten out of here too. And if you were interested in that sort of data, reach out to us. Okay, so that was tactic proofs. We're also going to look at term proofs. Even though our model is designed to predict tactics, we're going to show that by extracting data out of the term proofs, we can significantly improve the performance of our model. And as I said, Lean always stores a proof in this term proof mode, or this term proof form. And as I also showed, when you have a term proof, if you take a sub expression, a subterm of that term proof, and you mask it out by putting an underscore in Lean, what Lean's going to do, at least in many cases, what it's going to do is it's going to say, oh, the thing you need to put there to finish that proof, it'll tell you the goal and the local context. And that really is like the exact same sort of tactic state that we saw when doing tactic proofs. And we know what completes that proof. We know what the proof is of this goal, of this little part right here, because that was the thing that we just masked out. So we know what it is. And that leads to a very nice training set. And there's a number of ways we can use this data set. So let's go through them. The first way we can use this data set is to really just think about how can we augment our tactic data. So we know, I think many people know that neural networks are very data hungry, that they require a lot of data to train, especially if you're going to train them from scratch. But there are ways to augment your data set. And one way we found to augment tactic data sets is to use this underlying term proofs, because every time we have, if we know this term proof is going to solve this goal state, then if we just put an exact on the front, that is a tactic proof of that goal state. So that's one thing that we can add to our tactic data set. Now there's a few caveats here because this kind of comes from a different distribution and we don't want it to just prove exact every time. So we'll talk about how we handle that. Now these proofs can actually be quite long. So maybe this is silly to expect our model to do a whole proof in one go. However, we talked about the apply tactic, and what the apply tactic basically does is if you have a proof like this, where this is the outermost lemma that's used in the proof, the apply tactic says, okay, that's the outermost lemma. I'm going to apply that, and it'll make forward progress on the proof, and then it'll pop up a new goal or set of goals that you need to prove. So we also took all of these proofs that had an outermost lemma, and we added that lemma with apply in the front as a way to augment our training data. Okay, so this is our first set of ways to add, use proof data to add to our data set. And these are the most direct ones that where we're actually coming up with alternate tactic proofs. But there's other ways too that we can use our this data set more indirectly. So one of them is, instead of trying to predict the proof from the goal or the tactic state, we try to predict the proof from the whole proof term with that masked out part. And masked language modeling is a big topic in language modeling in general. And Google, the neural deformal team, specifically looked at with terms, with these very structured terms, you can exactly know when you're masking out like a whole subterm, and that leads to even better results. And they call the skip tree task, and we show that, or what we do it was with the whole proofs, and proofs are nice because they're even longer and they provide a lot of information and they're very clear on what you need to fill in here. And specifically, we're trying to do proofs, so that also helps. Besides the proof that you could fill in this, you can also just ask it, well, what is the type of this underscore here? And the type, again, because we're working in some sort of type theory, is the same thing as the goal we're trying to prove. So that's another task we add. Now, some models they'll have some kind of direct access to the library, and they'll search over all the lemmas in the library and decide which lemmas are most applicable to this. And our model doesn't do that. Our model has basically memorized the theorems in the library in some sense. But to help it do that, we've inserted some other tasks that help it kind of determine if a particular lemma is useful for proving a theorem. So by taking this goal, again, coming from the proof data, and the lemma used in the proof, we can then say this goal and that lemma, that's a useful thing. That lemma was used in this proof. So that's like a yes classification. And then if we take some arbitrary other lemma that wasn't used in that proof, then that's a no. So this is a form of classification, and it helps the model figure out what premises to use, or that's the idea. You can also do the same, something similar with the local context. So again, each of these goals has this all this stuff above it that says that, we know A is a proposition and H is a proof or a witness to A is true if and only if B. So which of those are used in the proof? And so then we have a comma separated list here of which of the premises are used in the proof. And sometimes some of them are, and sometimes some of them aren't. And our model is able to we train our model to distinguish which ones are and aren't used. In theorem provers such as Lean, they use a lot of newer programming language design principles that it's like the user doesn't really want to see all the nitty-gritty details. So there's a lot that's sort of hidden when you print out a term, but you can force Lean to print out a fully elaborated term where they turn off notation. So like this if and only if is now just a regular function that's at the beginning. It shows all these sort of hidden things that you need to actually apply a lemma. And then it looks kind of ugly, but it's helpful for, again, it's something we're trying to teach our model a little bit more about what's going under the surface of Lean. So we train it to take a proof and then predict its fully elaborated version. And the same thing with goal states. Take a goal state and predict its fully elaborated version. Tactic state, goal state, predict its fully elaborated version. And finally, again, because our model doesn't have access to the library directly, we train it to take a theorem in the library and predict the name of that theorem. And because Lean theorems are named usually pretty intuitively, it is a realistic task to ask it to kind of guess what the theorem is, the name of the theorem is. So we're going to train our model on all these things together. And this works well because we're using this auto-regressive generative language model. So the same model handles both the input and the output, and it can recognize similarities in the languages used there. But we do want to use different keywords for different tasks. so that our model realizes that they do come from a different distribution. So for example, we use this next lemma keyword and the proof term keyword for these tasks where we're augmenting our tactic data set. And then different keywords for other tasks. But we're going to train it all together. And I should step back. Some of you have probably more experience in machine learning than others, but this is actually a big thing in machine learning nowadays, is this idea that even if you're trying to train a model to do something, like predict whether there's cancer in this image, this X-ray image, it's helpful to pre-train the model or to co-train or to train the model on some other task at the same time, like whether that's a picture of a cat, whether something else is a picture of a cat. And it turns out to be really good. And maybe one analogy I think I heard in a previous talk is, if you go to school for mathematics, then it helps you in law school. And it's the same sort of idea, like the model seems to like pick up on stuff that helps it in other tasks. Now this would be fine, what I've shown so far as a data set and tooling, if we were just going to suggest to the user tactics to apply. But we really want to make this more of a full theorem prover. And for that, we need more integration with Lean. So we're going to train a model that predicts tactics from the goal state, but that's not as helpful unless we can plug that new tactic back into Lean. So we need a way for Lean to parse this tactic on the fly and to then apply that tactic and then get a new goal state and tell us what that goal state is. And then to go back in and loop over this process. We also need a way to do a tree search, because we saw that our model and pretty much every similar model out there isn't going to get things right on the first try, or not always. So we need a tree search, and we're going to implement a breadth first search tree search. And both these have been done in Lean metaprogramming, because Lean has a nice metaprogramming language. And that'll allow us to search for a proof. Oops, sorry. A little bit more about the proof search. So given a goal state or tactic state, we're going to query our model a certain number of times to get back a number of different suggestions on tactics. And then some of those might fail, but those ones that succeed, if they don't automatically solve the goal, then they'll go into a queue, and at the next level, we'll start to go through that queue and repeat this process. So this is basically breadth first search. We're going to do it up to a fixed step D, and to prevent combinatorial explosion, we're going to restrict the size of the queue. But other than that, it's basically a breadth first search. Okay, so our model is based on a similar model of that OpenAI did for the MetaMath theorem prover, which they also called GPT-f. And both that model and this model, they're coder-only transformers, which are similar to GPT-3. Now, I should mention probably one of the things that you've heard about GPT-3, if you've heard it, is it's very large. Our model isn't near as large as GPT-3 or even the larger GPT-2 model. It's 837 million trainable parameters. And it was first pre-trained on Common Crawl, which is just a general collection of English language sources from the internet and other sources. And then it was trained again after that on WebMath, which is a collection of GitHub, archive math papers, and Math Stack Exchange. And it's been shown both in this paper and our paper that training on WebMath significantly helps the performance of this model, even though WebMath is roughly informal mathematics and ours is formal. And we did check that there isn't Lean code in WebMath, so it's not a matter of data leakage. We split our data based on the theorem name, and that allows us then to keep all the proof data separate from the theorems that we're going to test on. And we train on all of the data at once. So this is this proof artifact co-training that was in the title. This idea that you don't just train on the tactics, but you train on lots of data that you get from the proofs that Lean generates automatically from the tactics and other and users who wrote tactics. And we're going to train all this together, and we're going to evaluate by trying to prove the test theorems and using a breadth-first search to prove them. Now, there's a lot going on in this table, and I encourage you to look at the paper if you want to get all the details. But the main thing to take away is this line in bold right here, and that's when we train our full model using all the different data sets, we get in the test theorems we prove about 48% of them, so a little short of half of them, which I think is pretty good performance. We were also wondering, like, how important was it that we were using these other data sets? And so if we just train it without the other data sets, with just the tactic data, the human written tactic data, well, then you only get 32%. So there is a significant improvement by using these other data sets. Another question of ours was, how important was it to train at the same time with these other data sets? Or is this a case where we could have just trained it beforehand with these data sets, like we did with WebMath, and then later trained it with the tactic data? And so that's right up here, and it doesn't do as well. So it is important to train at the same time, to co-train.
Jason, can you say one more time what mix 1 and mix 2 were?
Yeah, sure. So mix 1 is mix 1 is the two data sets that are just like augmenting our tactic proofs, where we just take the term proof and we put it an apply or an exact on the front of, or we take the term proof and put an exact on the front, or take the main lemma of the term proof and put an apply on the front. So it's kind of obvious that mix 1 would probably help, because you're just adding proof data. Where these other ones, these are like totally different tasks that are related, obviously, because they all deal with the Lean theorem prover, but they're not theorem proving tasks. And so, and then we did show also that that it helps to have both. So we did trained somewhere in here, yeah, right here, we trained a model that just has mix 1. So just the augmenting of the tactic data. And that, again, doesn't do as well as adding in these other auxiliary tasks like elaboration and premise selection and things like that. Lean.
Do you have slides that show the improvement you get by training at WebMath first? I mean, like the examples without using.
I didn't. Just I didn't want to take too much time, but it's in the paper. I can send you a link to that. Oh, actually, if I recall, in the paper right now, we don't have the raw numbers. We just show, but we do show an improvement in these numbers, which are more internal numbers to the model that are a measure of how good they are. But I think later on we're going to add actual like percent proved, but we don't have that right now. But based on these other numbers, it's not going to be as good.
Yep.
Okay, so this shows for each of the different libraries in Lean, in the MathLib library, how well our model does. Red is our fully trained model using all the data sets. Blue is our model using the tactic data set and the data set which directly augments the tactic data set with these apply and exact tactics. And then orange is just using the tactic data set. And then green is a baseline where we use this tidy tactic built into Lean, but we beefed it up a little by also making it behave as a breadth first search. And you'll see that some areas like logic we do very well. Other areas like ring theory, field theory, measure theory, it still can prove 20% of theorems, which I think can make that a useful tool nonetheless to users, but it doesn't have the same level of performance. We looked over a lot of the examples that we got from evaluating the model, and we discovered a number of cases where the Lean GPT-f theorem prover discovered a proof that was not was a lot shorter and simpler than what was already in the library. And in many cases, we actually swapped that out with this new proof and put that in the library instead. So this is one example where the proof is much shorter. There were some other examples that you can find in the paper. For sake of time, I left them out. But I think there were certain cases where users thought that the proof that GPT-f found was creative, and also the GPT-f proofs are pretty good at premise selection, of basically finding the right lemma at the right time needed to solve your theorem. Whereas the lean user sometimes just hacked through it because they didn't know that this lemma existed in the library. And so that's really good, because I think premise selection is one of the biggest needs just in theorem proving for a user, is just what is the lemma that I need to use to apply at this moment.
Jason, does your system know about the ordering? So like when mathlib things are in a certain sequence and the dependencies have to go backward. And do you ever find cases where it tries to use something forward?
Probably. So our evaluation knows about ordering, right, Jesse? I want to make sure I say that correct. Our evaluation forces that you can only
it sets
use
the runtime environment. So if it tries to use a theorem from the future, which it might because all the training data is like shuffled, the evaluation harness will fail instantly.
And how often does that happen?
I haven't measured specific numbers, but so I mean, if it's a theorem that's proved really early on, like a really basic lemma about like lists or something, then like most of the examples where it's prompted with the type will probably just use the name of that lemma to resolve it instead of replaying the proof. So one can imagine that it would be biased to just try using exactly that lemma instead of reproofing it.
Yeah. So like I said, there's some more examples in the paper, but I didn't include them here. So that's what we have to talk about. And thank you for your time. And I would really encourage you to try out the GPT-f tactic if you're interested in using lean, or if you're interested in machine learning for theorem proving. And you can find it here. You can find the paper here at this link, or just Google this title. I believe this talk will be on YouTube at some point. And feel free to contact us if you're interested in learning more about this project or the data sets that we have for the project. Thank you.
Thanks. Thanks, Jason. This was great, very clear and detailed. And I can add that I did myself try the GPT-f. And if you have a lean setup, it is quite easy to try it. Are there questions from the audience?
Yeah, can I ask a question?
Yeah, sure.
Yep. Okay. So, so the fact that training on web math does anything at all is just amazing. So I guess my first question is: you said how useful it is. Or you had some measure, I think. So how useful is it? And then the second question is: if training on informal mathematics is helpful, would one expect that training on other formal libraries like the Isabelle library or some Coq libraries or something like that might somehow be helpful?
So your first question was asking for a quantity of how helpful it was?
Yeah.
I don't remember the numbers offhand, but so this number is the what's called the loss of I believe it's the loss of the network when we train it. And without web math, I believe lower is better. It jumps up to, I think, like 1.07. So it's worse than a lot of these. We haven't. I don't have the numbers. Maybe Jesse does, but I don't have the numbers for exactly how many theorems are proved.
Well, let me add that it might be interesting to split web math up into pieces that are mostly formulas and pieces that are mostly text, and look at the separate effects. Yeah.
I can't remember. The MetaMath paper might have done that already. I'd have to look. I don't remember the details. At some point, these ablation studies are really great, but they do require a bit of a computational budget. So you have to kind of decide what you want to break up.
Could you tell us a whole training run, one of these, say your largest run, how much compute resources did it need?
It's in the paper. I don't remember the exact numbers. It's not something you'd be able to train on like a single machine.
But like days on 10 TPUs or days on hundreds of TPUs?
Well, it's not TPUs. I know, Jesse, do you remember the numbers offhand or have a?
Yeah, I just pulled it up. Let's see. Fine tuning on the full PACT set, so mix 1 plus mix 2 plus tactic, required 26 hours using 64 A100s.
Okay.
So it's not
Yeah,
terrible.
it's not so terrible.
Now, Jeremy, to your other question, whether incorporating other data like other theorem provers, I think that could very well help. And there's been work, I believe it was by Facebook research, showing that you can actually translate from say like Python to C by training a model sort of like this on both of them. And there's special tricks that are used for also just translating from like French to English. And so, it is very possible that you could get an improvement, and even better that maybe you could learn to translate from one library to another, especially in areas where they have common vocabulary.
Nice.
I had a question. So I was wondering if you could do some kind of reinforcement learning where you use your model and like ask the which works and train on the data generated by that. Do you have any thoughts on using reinforcement learning?
I'm sure reinforcement learning would improve this model. Now, there's two caveats here. Like the simplest sort of reinforcement learning, and the one done in the MetaMath paper, was you ran your model and tried to reprove your test theorems, or your training theorems, and you get different proofs. And then you can use those to train your model, and your model learns different things. And you can also use it to train your model to say, oh, this tactic isn't going to work in this situation, or this tactic is going to lead to or this goal isn't going to work. And then you can use that to as additional data for your model. And at least in that paper, they called it expert iteration. So now there's more advanced reinforcement learning ideas too that you can apply. One kind of trade-off is this model is sort of a heavier model to train than some. So you wouldn't have as many like iterations as say like an AlphaGo sort of thing where you're just constantly like running your model, generating data and retraining it. But for example, the neural deformal research did exactly that sort of thing. And they showed that they could, even with theorem statements, generate a theorem prover without even the proofs itself by just having the model learn proofs. So I think some sort of reinforcement learning would definitely improve this. Part of our point was just trying to show that this other thing also helps, and probably combining the two areas would help even more.
Maybe you said this, was there pre-training before the web math step, or is that just a totally raw model?
We used Common Crawl before this.
Okay, okay, so it really is the link, yeah.
Yeah, no, I think,
But that was it, that was the start. There was nothing before that.
I believe it was Common Crawl. Now that only before that, right, Jesse, that you know of?
Yeah, so all of the models in this plot are like forked from that single Common Crawl pre-trained model.
Okay.
And then they're all trained on web math.
Yeah.
Which is kind of a nice economy of scale because OpenAI, for their own purposes, research purposes and business purposes, took the time to train these models, and then we can use them, half pre-trained, so that they're at least somewhat better at basic stuff.
More questions? Okay, well, if not, let's thank Jason again for really great talk, and thank his collaborators as well for their great work. Okay, well, thank you.
Yeah, Jason, thanks a lot. I've long been skeptical about your sort of machine learning and theorem proving, but you make it increasingly hard to be a skeptic. So
Yeah, I think it's definitely the future, but there's a lot that needs to be done. And I think, even from your point of view, from like the philosophy of mathematics, I think there's a lot of interesting questions there of just what is mathematics in a practical sense, and how can we use that to further train these models.
Okay.
Jeremy, now you have no excuse not to sign up. So I haven't
I
gotten your email
will.
yet.
It's high on my list. It's high on my list. My big excuse is that I'm finishing a textbook. So
Good excuse.
Yeah.
Okay, I'm gonna sign off. But.
Okay, well, thanks. So,
Goodbye, Jason.
bye-bye.
All right. Take care, Jason.
So next week we'll have Ido Kaminer, who will speak about the Ramanujan machine, which is a computer system for generating conjectures about that relate to fundamental concepts. So I hope to see you all there. And thanks for attending.
Okay. See ya. Thanks.